in this lecture, we are going to discuss how to test mechanical properties of carbon fibers when we fabricate them. So you know that mechanical properties are very important to us. If you want to decide on the applications of certain carbon fibers, or if you just want to purchase them, there are two things that you will look for. Number one is the Young's modulus, which is the slope of the stress strain line in the elastic region, and number two, the ultimate tensile strength. This is the load at which your fibers will break. Okay, so if I fabricate, let's say, a new set of carbon fibers, I tried out a new polymer, or I tried out some other special heat treatment conditions, and now I want to see how different are these fibers. Are they better than the commercial fibers or not, or any other information that I want to have for these fibers. I need to perform these two tests to find out the Young's modulus and to find out the ultimate tensile strength. So how do we do that? At lab scale. Okay, these tests are relatively simple. In fact, those who have done their bachelor's in mechanical engineering may have already performed these kind of tests in the lab. You will typically take, let's say, one mild steel rod, and then you will use a setup known as the Universal Testing Machine, or UTM. That is the common name, but there are also related instruments, and there are several in-house instruments also. So the name is not that important. The idea is that this is a setup where you basically clamp your rod or fiber and pull it, and basically the load at which it breaks, your machine will actually measure the load and will also measure the at which point did it break. So the mechanical behavior. Also, it will measure the stress strain curve. So you will see that this is the slope. Then you can measure it later on. But what are these equipment doing, and what are the how do you actually calculate these properties and not just get the data from the machine? That is what we are going to learn. So as I said, that you will use the similar kind of setup that you would also use for a large scale material. Then what is the difference? Well, in the case of fibers, our sample is much smaller. Also, the loads that we apply, especially if you're performing the test for a single fiber, then the loads are much smaller compared to what you would use for a thick steel cylinder or rod. So that is one difference. The loading of the sample also becomes slightly different, because you may not have the same kind of sample holder. So in the case of steel rod, you will just have two clamps, and then you will very tightly clamp your sample or specimen. But in the case of carbon fibers, you may have certain chip-like structures and smaller sample holders where you can glue your fiber, and then you can load this entire chip into your UTM. So there are some fundamental differences, but as such the calculations remain pretty much the same. Okay, so the chip that I was talking about, it looks something like this. This is just a schematic again. What you have is, you have a fiber, straight fiber, that is clamped on both sides. And how do you do that? In this particular case, you will glue it, you will wax it, and then let it dry for a while. So that glue, you can also use epoxy resins again. So this is what you're going to do, and you grip your fiber, you have it tightly, and you have it under complete tension inside your chip. Now you also see something known as the gauge length. Gauge length is basically this is the length which is actually being measured. So between your clamps, this is the actual length of the fiber that is being tested. Okay, and then other things like gripping area, and this tab or chip, it may be made of plastic, it may be made of paper also. Okay, so this is the first thing that you will have. Now you will load this entire thing into your UTM. You will typically have specific slots for such tabs, and these tabs or chips also, you can buy them specific to your setup. Okay, now one interesting question for us, and the most important question for us, is that do we use single fiber or the bundles of fibers? So there are pros and cons of both. It depends also on what is the scale at which you want to have your application. Do you want to use the bundle of fiber for your application, especially if you're doing any manufacturing application? You want to, let's say, make composite materials out of it, or you already have some resin in your when you were making the bundle. In that case, you will rather use the bundle because that is sort of more realistic. But if you want to test the mechanical property of single fiber for whatever application you have, in that case, you will use the single fiber. Okay, so the bundle is basically this rope that I'm talking about. Single fiber tests are, they can be time consuming. And there is one more thing, your fibers must be uniform. If you're testing single fibers, in that case, most of your fibers, the diameter range of your fibers should be pretty much uniform. So this will often happen when you're when you have mesophase pitch based fibers. So in that case, what you're using melt spinning technique, and melt spinning gives you thicker fibers, but they are more uniform because they are coming out of the spinneret, and the capillaries in your spinneret are all of the same diameter. So you pretty much get your fibers which are also more or less of same diameter, but that may not happen in the case of electrospinning, because using the standard electrospinning technique, you know that you end up getting this range of diameters in your fiber. So if you now test a single fiber, then in that case you need to be very careful that you test the fiber that has the average diameter. So if you have 100 to 400, whatever is your range of diameters, which can be very easily calculated using the scanning electron microscope, and even there are other techniques. I will also discuss them briefly. You can easily, nowadays there are so many image processing software available, many of them are also free. They can actually tell you, they give you the information about what is the average diameter of fibers in your sample. So in that case, if you want to test a single fiber, then you should take the one that falls in this average diameter range. Okay. Other than that, well, in general, if you want to utilize single fibers for a certain application, definitely you can perform the test on a single fiber. However, you need to know how realistic it is in terms of your application. Okay, now if you test the bundles of fibers, okay, it is more realistic. This is how you're going to use them for your manufacturing applications. But there are also issues with that. For example, you may, and the fibers may get entangled. There may be twisting of fibers. So you may not have all fibers. You need to have them in tension, right? So you need to have them straight, but that might not be the case. Some fibers may get, entangled, and hence you may not be able to get the right values from that. So this is also another, there may be also certain friction between the fibers. Again, you can get rid of the friction by having some resin or some polymer between them, some sort of lubricant. But if you don't want to have the lubricant and you want to test the properties of your virgin fibers, in that case, you may also end up having some friction between the fibers. So these are some of the problems with the bundles, but then you need to choose what is important for you. Okay, so now we come to the procedure. How do we do that? So as I already I have shown you this chip. What you do is you prepare your fiber specimen and you load it onto the chip, and the chip is loaded onto the machine on your UTM. And now you need to align the axis of your fiber with the crosshead. So again, these are certain operating conditions of the machine, and I'm not going into the details, and every machine may have different set of operations, and how do you align it, and what kind of crosshead you have, and so on. But what you need to do is you basically need to align your fibers with the axis of your instrument. Then you apply the load, and apply the load till your fiber breaks. So apply load till fracture. Okay, so that is that. What do you do afterwards? Now, how do you calculate the values from here? Here is the typical load displacement curve that you will get for your carbon fiber specimen. So what you see in these load displacement, the first curve, for example, you will have an elastic region. Okay, this is also interesting that in the case of carbon fibers, you will typically get an elastic behavior before they break. Okay, but here and there towards the higher end, you may have certain strain hardening. So you may see certain strain hardening because the polymer chains realign, the carbon chains realign themselves. So this is always the case. You get strain hardening in the case of viscoelastic polymers as well, that we had learned before. What happens is carbon fibers are not like polymer fibers. They do not have the same kind of geometry, however, or the microstructure. However, they do have these long sheet and chain like structures. So they do tend to at some point align themselves, and therefore you may get a little bit of strain hardening, but typically even that is not very significant. Typically you will get an elastic sort of behavior. So as you increase the load, the displacement will also increase, and at some point, yield point, your fiber then will not behave elastic anymore, and soon after that you will have the fracture. So unlike the viscoelastic polymer where you have a larger region of strain hardening, that is not the case with carbon fibers. Only if at all you see it, it's not going to be very significant. Okay. So these are the kind of curves that you will get from your machine, and here I have mentioned a few things, a few terms that I will be using for showing you what is the, how do you calculate. So Young's modulus from these curves, how do you calculate? Your Young's modulus is L divided by C into A. Now A is the area of your specimen. Make sure that it is in millimeters square. Actually make sure that all the units are, as they are units are always a problem when we do these kind of calculations, right? So A is your area and L is the length of your fiber that is being measured. So you can call it the gauge length. Now what is this term C? C is calculated now by these graphs, by these plots. Okay, so C equals what is known as CS minus CA. Again, I will tell you what is this. CA is the indicated compliance. As you can see here, I have written it. Indicated compliance that you can see in your second plot. Which is what? How is it calculated? This is the expression for it, I into H divided by F into S. And what are these terms? Again, you can read in this glossary. Your I is the full scale elongation. H is the crosshead speed. So this is, again, these are very instrument specific parameters, but I'm just trying to show you this is how it is calculated. F is your full scale load, and S is what is known as the chart speed. So these are the parameters that based on these things, it is then the CA value is calculated, and CS is nothing but the y-intercept. In the second plot that you see, indicated compliance, there you see there is a certain intercept after which you start getting your values. You need to factor that in. So that you need to subtract, and so this is how you will get the value of C, which is CS minus CA. And now you insert all the values in your Young's modulus expression, and that is how you will get the value. Okay. Now the second property for us, important property, is the ultimate tensile strength. This is very easy to calculate because you will always know what is the load at which your fiber breaks, and just that load divided by the cross-sectional area of your fiber is what will give you the ultimate tensile strength of the fiber. Okay, now there are some more curves. Again, we are still on the same topic of the modulus. Here in the second curve, you can see that there is a certain, so the linearity is sort of compromised a little bit. That is because of the strain hardening, as I mentioned before. What is now important for us is that different types of carbon fibers have slightly different behavior. Why? Because they have different crystallinity. So if you take pan-based fibers, you typically have turbostratic carbons, right? You know what is turbostratic again? You have the carbon sheets, but they are still randomly oriented on top of each other. They are not graphite-like crystallite. They do not have A-type arrangement. However, when you get your fibers from mesophase pitch, then you have them more graphitic, and that means that you at least have some regions of A-type crystal structure. So in that case, you can imagine that you have a higher Young's modulus for these kind of fibers, for mesophase pitch or the graphitic type fibers. Why? Because you have nicely aligned sheets. They behave more elastic. If you give them certain strain, they may change their position slightly, but then they will try to come back because the molecular attractive forces are pretty strong. You have a good crystal structure. So the crystal structure always tries to come back to its normal position, and hence you here will see it's a good elasticity. Higher value of elastic modulus is what you see. That is in the case of when you have graphite-like crystallites. But when you have turbostratic sheets, now these are randomly oriented sheets. Randomly oriented sheets means they may also contain some non-6-membered rings. That also means that if you distort them, they may not be able to come back to their normal position. However, at some point, if you keep on distorting them, maybe they will find some new normal position, or they will try to realign themselves. That is what we call the strain hardening. So this is sort of the mechanism, and this is the reason why you get better elasticity or better modulus in the case of graphitic fibers. Again, it depends on your application. What is it that you want? For many applications, for many manufacturing applications, actually you want a good modulus, but biomedical applications, for example, would require a good ultimate tensile strength. So for example, if you are making bone implants, you might want your structure or your bone implant not to be too stiff, but rather, because you're not applying too much load there. What is more important there is the flexibility. What you want is that your fibers should be able to, you should be able to press the overall structure a little bit. Okay, so here then I have written, this is like a summary that your some carbon fibers, especially pan-derived carbon fibers that have more of a turbostratic arrangement of sheets, they have a higher value of tensile strength, while the graphitic carbon fibers or graphite carbon fibers, those derived from mesophase pitch, will have a higher stiffness or higher Young's modulus. Another important property, you know that for all these calculations, what you need is the cross-sectional area of your carbon fibers. In the cross-sectional area, if you have a single carbon fiber, and that is thin enough, then it's easy to measure just by using scanning electron microscopy. You can just take a picture of that. However, if you're using a fiber bundle, and that bundle may not have a perfectly circular diameter, and it is probably in the millimeter length scale, the diameter. So in that case, you may need to use some other techniques, because it may even be beyond the field of view of your scanning electron microscope. In that case, what do? We use optical microscope first of all for taking a basic image. So you will, for example, take 200 times magnification, and then you will capture an image. Some of the UTMs are also equipped with the microscope. You use this formula to calculate your cross-sectional area. So now what you see, the important thing here is that, okay, AF, the first term, that is your, that is just the area of a single fiber. What is important here is you are dividing this entire thing by the magnification factor. So how many times, which is 200 in this case. Okay, and N is the number of fibers that are under observation. So this is pretty much for a bundle, for a relatively sort of thick bundle of carbon fiber. Okay, so this is how you calculate your cross-sectional area. Again, you should look for the units and have the right units. Okay. Now the diameter measurement, as I mentioned, for the single fiber can be done using SEM. So you see, this is an SEM image. Scale bar is 400 nanometer. You can see that these fibers, they are electrospun fibers, and you can already see that they are not really uniform. So some of them are, let's say, about 100 nanometer, and some are 300 nanometer in terms of diameter. So in that case, you will need to calculate the average diameter of your fibers. But you can use scanning electron microscope for this purpose. Okay. There is also something known as laser micrometer, where what you're doing is you're scanning you have a laser beam, and then you have the fiber. So you're shining the laser on top of the fiber. Now the region where you have your fiber, let's say this is your fiber, and the laser is shined from here, then the region where you have the fiber, you will sort of get the shadow of this fiber, and that is how you will measure the diameter of the fiber. So that is known as a laser micrometry. That also you can perform for a single fiber or a bundle of fibers again. Then there are also many other methods which can be used for, even laser micrometry can be used for if there are any visible voids inside your fiber, then you can also use that. Or there are gaps between two fibers, as you can see in this SEM image. If there are gaps between two fibers, there also you will, the laser will pass through that gap. So based on these things, you can, but of course the laser wavelength has to be optimum so that, you can get a good contrast in your image. But these are some of the techniques that you use. What you also use is, yes, transmission electron microscope. So here is an image of a carbon fiber. For measuring a carbon fiber using transmission electron microscope, you will first of all typically not do it just for diameter measurement. You will typically use transmission electron microscope only when you want to see the microstructure of the fiber, how the chains are aligned, what is the, how does it look inside. And for that purpose, you also need to have very thin fibers. You know that the fibers, if any structure is thicker than 20 nanometer, then you will typically just get, it is too thick for TEM. So you will get like just a black image and you will not be able to see much. But here in this particular case, you see that the fiber diameter is approximately 20 nanometer. And you can see how the chains are aligned. Actually, these are the chains that I call turbostratic. So you can see that these are these wavy chains. And if you actually measure the distance between these chains, then it is not it is higher than what you will get for ABAB type graphite crystals. So these are some of the methods for calculating various values for carbon fibers. Again, this depends on your very specific equipment and specific specific measurement technique, specific type of carbon fibers, whether you want to do it for single or for a bundle of fibers. You can accordingly choose your parameters, and you can accordingly choose your specimen as well.
Okay, so now we are going to solve one numerical problem, and after this hopefully it will become more clear to you whatever we have learnt in the class today. So you know that we have the ASTM standard methods for mechanical property testing. The one that we are going to use here, the protocol, this is the number of that protocol, D33795. So you can also search for it yourself, and then you will actually find more detailed analysis. So in case something is missing in this problem, then you can find it here. Okay, so what are the things now that are given to us? Okay, so first of all, we have these fiber diameters, fiber areas, so cross-sectional areas, which are the values of AF. So we will see when we write down the formula. What do we have here? 100, 80, 50, 30 and 90. By the way, we have taken only 5 fibers here because this is just an example. But when you're actually, when you're actually doing the experiments, then you should take a minimum of 10 fibers. Okay, so this is one thing that is given to us. What else? We have the failure load, okay, which we will require when we want to calculate the ultimate tensile strength. What else do we have? We have the true compliance of the system. Now, true compliance, I'm not calculating here, the value is already given to you, but you generally have to calculate it for your specific system. So here the value is given to us, okay, which is 0.05 millimeter per Newton. Okay, what else? The gauge length. Gauge length is very important. Gauge length we will write as L. So this is very important as well. So generally you will take it between 20 and 30 millimeter. But also by changing the gauge length, sometimes the final answers of the Young's modulus that you will get, that will slightly vary. So this is also an important factor. Okay, what else is given to us? The magnification factor of your micrograph. So that is 200. Okay, so now let's do the first calculation. We need to calculate the Young's modulus, and also we need to calculate the ultimate tensile strength. In both cases, what do we need? We need the average filament area. When I say average filament area, this means this is the test filament. Test filament means this is the bundle or the rope that you're testing. So filament here does not mean that this is an individual fiber. Okay, you can also do the testing for individual fibers, but that is slightly different methods are used for that. So here we are talking about a filament which is actually a bundle. So this filament area, or A, you also see the term AF, that is what we are going to calculate, and that is what is useful for all the calculations. What is the formula again? We have the summation of all areas, but these areas, individual fiber areas, they are taken in millimeter square, and what is given to us is in square micrometer. So we have to factor in some 10 power minus 6. Okay, and then there is another 10 power minus 6 which is already there in your formula, and that is because we get the area values finally in square meter. So that is why we already have one 10 power minus 6 factor here. Okay, what else is there in the formula? Now here we need to enter the value of n, which is the total number of fibers. So let me just write the total number of fibers. This is the n. So here we have just taken 5 fibers and then the magnification factor. Okay. So now from here, you will write down the values AF, so 100 plus 80 plus 50 plus 30, 90. And then after all of this, I have calculated the value of the area is, so it comes out to be 1.75 into 10 power minus 9 millimeter square. So I have already done the conversion from square meter to millimeter. So these conversions are something that you have to be careful with. Okay, so this is the value of the area. Now we will do the rest of the calculations. So number one, we need to calculate the, let's first calculate the Young's modulus. So Young's modulus, the formula equals, this is basically your L divided by, L is the gauge length divided by the true compliance into again the area that we have calculated here. So this will equal L, you remember, is your 20. It is in millimeter, and also in the formula we need it in millimeter. And then the value of true compliance also, this is given in millimeter per Newton, which is the correct unit that we use in this formula. In case it is not given in the correct unit, then you need to change it. Okay. What else? The area again, 1.75 into 10 power minus 9, and here we take it in square millimeter. Okay. So what is, so the value of Young's modulus that I have calculated comes out to be approximately 228.57 gigapascal. So this is your solution to the first part. The second part is the calculation of ultimate tensile strength, which is actually the easy one. All you need to do is the failure load, which is already given to us, divided by area. So failure load is 5 Newton divided by again 1.75 into 10 power minus 9 square millimeter. And the, the value that you will get from here will be 2.86 into 10 power 9 Pascal, or 2.86 gigapascal.